This talk is about perception systems for autonomous vehicles using energy-efficient deep neural networks. I'm Forrest Iandola. This is a presentation that a lot of people have contributed to over the years, but in particular, Ben Landen, Kyle Bertin, and Kurt Keutzer of DeepScale, as well as some of our other colleagues. I owe a lot of credit to them for putting all this together. So diving in here, I'd like to kind of just level set on terminology. So when we think about an autonomous vehicle, there are a lot of components to that, and some of them are still being defined and figured out because it's a pretty kind of emergent technology area. But broadly, four of the most critical pieces of an autonomous vehicle are sensors. So naturally, this being an imaging conference, we know lots about that here. You probably know more about it than me. Those sensors serve as inputs to a variety of other systems in the car, most critically the perception system. So perception, some people call it computer vision. I like the word perception because it's sensor agnostic. So applying algorithms to make sense of going from pixels and bytes to what really is the semantic content of our environment as well as its 3D position. The complement to that is high definition offline maps. So those maps typically, they're in 3 dimensions, as much as can reasonably be annotated of the static objects in the environment have been. So things that don't move very often, like the lanes and the signs and so forth, should be on the maps. And then naturally there's an interplay between those two where the perception system captures the dynamic objects which get superimposed onto the map. Together, all this forms an environmental model which goes into the path planning and actuation system, which figures out where would we like the car to go and how do we manipulate the car's actuators to accomplish that. So naturally, so our company, DeepScale, focuses primarily on the perception piece, and that's what I've been invited to talk about here today, so that's what I'm going to do. And so let me spend a few minutes on what does a car really need to see to drive. And this is sort of an unbounded problem, because as humans, we know that as we drive, there always are more things we could look at, more data that we could uncover around us to further improve our driving decisions. So here I'm just going to start with the basics and leave it to your imagination to fill in all the other things that I don't have time to give as examples. So this is really small because it's actually a very kind of fine-grained problem. So you want to detect all the critical dynamic objects. So you have non-vulnerable objects like vehicles, which, vulnerability is sort of a continuum. The most vulnerable objects tend to be unprotected pedestrians, motorcyclists, and bicyclists, where if you collide with them, there's a very high chance they'll be seriously injured or killed. Vehicles that have occupants in them that are moving around are much less vulnerable to injury, although it's still a big concern. Parked cars, for example, you don't want to hit them, but the damage to human life is going to be lower. So you kind of have this taxonomy of the vulnerability of the object as well as its category, vehicle, pedestrian, and you could divide it into hundreds or thousands of categories potentially. You want to track the objects and figure out their range from you. So how far away is it? And ideally, to put them in 3-dimensional space. Here, for simplicity, I've just drawn rectangles, bounding boxes. But what you really want is a 3D box for each object with its extent, its roll, pitch, and yaw, and so forth. So you have as much as, up to depending how you think about it, a 6 to 9 degree of freedom object detection problem with how far away it is, what's its 3D box, and what's its roll, pitch, yaw. And then you start to think about where can I drive? So here, the darkest green is where my current lane is. The lighter green is where else can I currently drive safely and legally. And then the yellow on the other side that is road, but it's actually not drivable road for me because it's out of reach for me, and it wouldn't be legal for me to go this direction in those lanes. So this is just one of many example problems that can be framed as what we call semantic segmentation, so labeling every pixel based on what object category it's a member of. Here, for simplicity, we're just showing different types of drivable area, but naturally, everything in the scene could be labeled in this manner as some sort of semantic category. And then, just for completeness, you also want to know where the lanes that the ones you're in, the other ones that are available, where's the center of the lane that you're looking at. And an interesting thing about this is, well, there are lots of papers on how to do this sort of thing, but one challenge that I'll get to in a minute is it's hard to do all this in a limited computational budget. It's a lot easier to do this with a trunk full of state-of-the-art computing servers costing hundreds of thousands of dollars. The other issue is, so there's another conference that runs every year called CVPR, or Computer Vision and Pattern Recognition, or ICCV, or there are others. So CVPR, there are lots of papers every year about how to solve problems like these. What's lacking is there aren't very many CVPR papers about how to combine a bunch of CVPR papers into a unified model of the environment. So that's something that I think currently is more kind of lore or trade industry secret sauce right now. And I'm not sure I have any kind of final resounding lessons on how to do that, except it's a lot of hard engineering work to get all this registered together, as opposed to just saying, got one model that knows about lanes, got one that knows about cars. They're just kind of different things. You want that all together. Right, so hopefully I've given you at least a rudimentary idea of what kind of thing you want to see when driving, in order to drive effectively. Naturally, this is just scratching the surface of the kinds of things you want to know. People from Waymo or Cruise would point at this and go, yeah, that's about a 1/100th of the overall complexity of what you want to see. I would agree with that, but it's hard to annotate all of it at the same time. Right, so I guess what I'm seeing right now out there is a lot of companies have built prototype autonomous vehicles that, at least in certain conditions, can drive reasonably well. But if you open up the trunk, you find a lot of computing power. So this is an image that was released by Audi maybe a year or two ago. This is what BMW and Intel were showing not so long ago. This is something from Ford. If you Google image search autonomous driving server, you'll find endless stuff like this. And naturally, Waymo, for example, is too secretive to tell you what's in there. But if you ever pull up behind a Waymo car, there's a little label printer printed sticker that says something to the effect of, "Please do not use trunk. It's full." Just bring your luggage and kind of put it on your lap or something. So I guess let's spend a minute on what are the implications of doing autonomous driving like this. So first of all, not just the trunk space, but big computers lead to cars being quite expensive. So I routinely see people talking about in this article $250,000 to fit a vehicle for level 4 autonomy with relatively limited range of operation, geofenced. And I've heard numbers even higher than that. So this makes the vehicle very expensive. Also, on a reliability perspective, these very high-end servers with GPUs are amazing technology, but they're not designed for automotive constraints, which automotive parts should last 20 years. In fleet operation, still should last many years. These parts are designed to run in the cloud in servers where they're obsolete in 3 years and thrown away, not 20, right? So there are lots of issues with this server in the trunk thing. Maybe most principally because of the cost, and secondarily because of the longevity, the reliability, the power dissipation required. And so that means we can't do this anymore. And so the first place a lot of people look for how do we reduce cost of autonomous vehicles tends to be sensors. That's coming down. There are lots of projections about how sensors are improving. There are people also who are doing more with cameras and becoming a bit less dependent on LiDAR, which currently is by far the most expensive type of sensor in autonomous vehicles. I feel confident that that cost curve will improve, and I feel like there's. I don't want to get into the full camera versus LiDAR debate, but I feel like you can take what used to be implemented in depth sensing hardware and move it to software and cameras if you try hard enough. So there are lots of ways to dig yourself out of that hole between better sensors and better software. But then the thing that blows up even more is even more servers in the trunk to support all that. So the place a lot of people look next to reduce the cost is how do we take those servers in the trunk and replace them with something that looks more like a few cell phones in its size and cost curve, power, et cetera. So I'm not the first one to think of this. Lots of companies, most principally I'd say NVIDIA, are pushing really hard on adapting their hardware in each redesign to be more centered on deep neural nets, which tend to be the most energy-consuming and compute-consuming piece of the neural net of the autonomous vehicle stack. Perception also tends to be the most compute-consuming piece of the autonomous vehicle stack, as evidenced by the fact that a lot of the control algorithms only really run in the CPUs, in fact. So these folks are pushing really hard. I think there's a lot of questions about, when will the AI chip revolution, where things really get skewed towards deep neural net accelerators, start? I would argue we're already midway through it. So, in 2012, we could do on the state-of-the-art GPU at the time, 3.5 teraops. This curve up to a at least theoretical claimed peak of over 112 teraops far outstrips Moore's law. And the way this happened is not so much about better transistors. It's about actually having a good chunk of this GPU dedicated to doing 4x4 matrix multiplies in low bit width math. So this, this fairly mainstream device, compared to startups at least mainstream device, does a lot of the tricks that most people have been talking about for years, commercializing in deep neural net processing hardware. Now, what's not so good is how little memory has improved in this time. So when you think about a computer system that will implement algorithms, say deep neural networks, what you want is to be able to feed enough bytes of temporary variables, of parameters, of whatever, to the processor so it can stay busy and get work done. So you can have this issue of being what's called bandwidth bound. So if you don't have enough memory bandwidth for your algorithm, no amount of compute is going to help, and you'll just wait around for memory to load. So the ratio of computation to bandwidth has gotten an order of magnitude worse with the advent of this hardware, because while from K20 to V100, the gigaflops per second improved by close to an order of magnitude, memory bandwidth only went up by about 4.5x, which is relatively kind of like nothing. Same issue in mobile and small devices. So if you look at what's back in the early days of deep learning, a lot of people from the group I was in at UC Berkeley worked on implementing deep neural nets on mobile devices as early as 2013. One of the devices we looked at was the fairly standard set of GPUs that ARM offers in mobile. And you get a computation to bandwidth ratio of 9.3, which is livable. You don't have to be that clever with your algorithms and implementations to get pretty high utilization of that GPU. But today, things are skewed at least as badly in mobile as they are in servers. So even kind of fairly relatively low-cost Chinese silicon like Huawei, they're doing neural net accelerators. They're using the same DDR4 technology that they were using last year before they had the neural net accelerators. That blows out the compute to bandwidth ratio quite badly. NVIDIA, Jetson, Xavier, they're a little cagey on numbers, but according to my friend Brian Catanzaro there, VP of Applied AI, one of my former lab mates at Berkeley, these numbers are more or less correct. And this compute to bandwidth ratio is the worst I'd ever seen when I started looking at this chip last year. So that's where we are now. And if not clear, the implications of this are the worse your compute to bandwidth ratio, the higher it is, the narrower the set of computations that you can do that will fully utilize the hardware. So what do the next generation servers look like? Where are we headed? So there are a lot of claims out there. We can take these at face value for the sake of analysis. We'll see what actually materializes. I see things talked about, between Mythic, Grok, and Sentient as just a representative sample of a newer breed of silicon companies that are focused entirely on deep neural nets without any need to cover things like graphics. they're claiming anywhere from 4 to 20 tera operations per watt. So the reason tera operations per watt is an interesting metric is, or sorry, really tera operations per second per watt. That's interesting because it's free of any constraints on what size is your device. It's just saying, given a 200 watt chip, you multiply that number by 200 to get how much you could theoretically run. So this is getting increasingly sort of speculative or estimate-oriented because we haven't seen this next generation of chips yet in the flesh for the most part. But I've reproduced the K20 and V100 numbers here. I've added a column about, we're now talking in tera-ops rather than giga-ops because things are moving forward that way. I've added a column for tera-ops per second per watt so that we can kind of abstract away whether we're talking about a small chip or a big chip wattage-wise. But let's say that we look at one of these chips that's claiming 20 tera-ops per watt for common deep learning operations. And let's say that we're looking at a device where half of the wattage is applied to that chip for computation, and the other half is applied to memory and other pieces of the system. So that gives us, for a 250 watt system, 125 watts to work with. 125 times 20 should give you 2,500 tera-ops per second, best case. But if you look at the trajectory that the memory industry is on, memory is only getting sort of doubling in speed per watt by, on a good cycle, 2x over about 4 years. So high bandwidth memory 2, which is arguably the thing that comes after GDDR5 or 6, or a higher end alternative, has been around in common use since about 2016-ish. And the projection is that in 2020, high bandwidth memory 3, HBM3, will come out and be twice as fast as that with all else, such as wattage, held equal. But if you go from that V100 to the 20 tera-op per watt theoretical device, and it's doing 2,500 tera-ops per watt or tera-ops per second, and you're just using the natural progression of memory to HBM3, you're talking about over 1,000 computations per byte. So you actually have to compute 1,000 things before you load the next thing or store the next thing to memory. And there's a very narrow set of deep neural nets and algorithms that actually meet that constraint. If you don't do that, it will still run, but it will be really slow. So from my perspective, to kind of conclude this section, what I see going on is, well, we asked, will the next generation of chips sort of solve all our problems, get rid of the server in the trunk, and so forth? And the answer is, I think it will help, but it's sort of an Amdahl's law issue where you fix one bottleneck and all these other bottlenecks, such as memory, emerge. And so I think the reality is, we're going to enjoy some benefits from these next-gen and next-gen chips, but we also have to dramatically rethink how we design our deep neural networks to take advantage of them and really, for real, deliver on that promise of going from multiple kilowatts of servers in the trunk down to something that's hopefully close to being negligible, that consumers could get their hands on easily in mass-produced vehicles. So I tend to call this concept, we've intermittently call it small neural nets, or sometimes we call it squeezing AI. So when I use the word squeeze, what I mean is to make an AI system use less resources by whatever means necessary. So by resources, depending on the system you're on and the constraints you're dealing with, those might be how much memory you've allocated, your memory footprint. It could be your memory bandwidth, how much data are you actually transferring between your chip and the memory that's near the chip on your board, but is actually off chip. How many computational operations? This tends to be the most popular thing to try to minimize, although, as I mentioned before, compute is getting very close to free, and all this other stuff is just as expensive as it used to be. Power and energy are very important. Power being kind of a hard ceiling on how much heat you can dissipate and how much your chip will actually draw. Energy being something to optimize. And then I look at time as a resource just like anything else. So how many frames per second, or how can we reduce the runtime of these algorithms? And then by means, we look at designing new deep neural network models that can be done manually or automatically. That can involve changing the neural net structure, which, as I'll get to, is something that can be partially automated. It may also involve inventing new math, which so far is more a human inspiration, an engineering kind of thing, than a fully automatable process. It can require, it can be benefited by doing quantization and pruning, which may vary in terms of the right scheme based on what hardware you're on and what your application looks like. We can implement it better. If you look at the actual libraries and frameworks that we're running, there's always room for improvement there. Often in a hardware, per hardware platform, you can make further refinements and optimizations to your implementation. And then finally, when you train, gathering better data and rethinking your loss function, other parts of your training can improve accuracy, but can also broaden the range of neural nets that will train correctly to achieve your desired results. And that range may grow to include neural nets that fit more nicely on your hardware. So let me do a bit of a review of, I showed what we want the car to see, at least abbreviated. We talked about why we want neural nets to be smaller. What do these two things actually, how do these unify? So most computer vision, or more broadly perception applications, rely on a relatively small set of core problem statements or core capabilities. So there's image classification, but for autonomous driving, a surprisingly broad variety of problems reduced to object detection or semantic segmentation. Detection being drawing boxes around objects, estimating what kind of object is it, what's the 3D position. We talked about this earlier. Semantic segmentation being classifying everything, every pixel or every point in the LiDAR scan based on what kind of object is this a member of. And more generally, these all are basically regression or classification problems. Detection being a little bit of an oddball in that you have to estimate a bunch of coordinates. But many of the other things we do, not just semantic segmentation, but say depth estimation, are basically tensor to tensor computation. So you input an image or multiple images or LiDAR scan or whatever, and then you output more or less the same data structure that's been annotated automatically by your model. You could even do that for estimating the depth or the 3D shape of the environment. So as a result, there's if you can solve one of these well with a good neural net, chances are you could train that neural net to do a bunch of things like this. But one of the most glaring problems, which I kind of foreshadowed earlier, is we need a very different kind of deep neural network. So models like BGG16 and ResNet and ResNext have been very popular. I think when you're looking at a cloud-based server environment, or maybe even a bunch of servers in the trunk, you can get away with things that are this computationally intensive, running at many gigaflops per image, even for relatively small images, potentially even blowing up to teraflops per image for large images. But when you look at embedded devices today, as well as I talked about earlier, the embedded lower-end devices of tomorrow, particularly with their constraints on memory bandwidth, this tends to really not be the right approach. So a few insights about what we want instead of this. What would be better? So one observation is speed, throughput, or how latency as well. It tends to be more related to memory accesses than computational operations. So basically, the insight is if you have to go off chip to retrieve something, and unless that you're retrieving something that you're going to use in the far future, that's just going to kind of take the whole operation, make it grind to a halt for quite a while. So that's an issue. Basically, talking to off-chip DRAM, or even worse, disk, is kind of the thing you just want to remove from your bag of tricks as much as you possibly can. Similar thing with energy. So this is a study by Mark Horwitz's group at Stanford. This is using older technology before the deep neural net revolution, older transistors as well as more basic just CPU processors. So, but just on that, there's a several order of magnitude gap between doing a computation and accessing something off chip. Accessing caches on chip also is not cheap, but it's much, much cheaper than going off chip. So anything you can do to avoid falling off your chip in terms of spilling load or having to reload parameters every image or things like that, is really, really good for energy and speed. And again, I think this has actually gotten worse potentially by at least a couple more orders of magnitude, this gap with the latest technologies. So this is something that, between Kurt Keutzer, who I guess I didn't really introduce earlier, he's one of the co-authors on this talk, but Kurt Keutzer actually is my former PhD advisor at Berkeley, and he's also my co-founder at DeepScale. So Kurt and I have been working on squeezing neural nets into small places for close to half a decade now. So by 2016, we'd already explored on the order of 10,000 configurations of deep neural nets. By configuration, unique configuration to me is a unique neural net architecture or topology, and also its training regime. So, in reality, more like 1,000 architectures, each trained 10 different ways. And we were super lucky to have access to a supercomputer at Oak Ridge National Lab through some friends at Berkeley that made a lot of this possible, because as you may know, compute tends to be one of the most important things to have access to when exploring the design space or when training neural nets, even if you're doing it pretty efficiently. So the punchline here was that, so at the time, the most widely cited and probably most widely used deep neural net for computer vision applications, definitely for image classification, but extended to other applications like detection, was AlexNet or models based on AlexNet. So you get about 80% top 5 accuracy in those days with AlexNet and have around 240 megabytes of parameters. With SqueezeNet, which was simply an entirely new neural net design that we came up with new layer dimensions, new organizations of layers, we got that down by 50x, so down to just 4.8 megabytes. And the aha here was, if you look at an embedded processor that might have on the order of 10 megabytes of on-chip memory total, not DRAM, not off-chip, but on the chip, you could store the parameters of the model, and you could store its temporary variables if you're running at a low batch size, like batch size 1 for real-time applications, and never fall off the chip. You just eat images, do all the processing locally, spit out the results, and you could unplug the memory, and it would still work. This, naturally, things have moved a long way since then, which I'll get to. But this was an immediate success in embedded vision. Companies ranging from the embedded hardware company NXP to Facebook and Qualcomm have showcased various SqueezeNet-based models doing great things. SqueezeNet has become part of the source code of most deep neural net frameworks now, and it's sort of a standard reference model that lots of people use as inspiration or even use in their work. But we didn't stop there, so SqueezeDet is a squeezed-down model for object detection, localizing and classifying objects and images. It's at the time won a Best Paper Award at CVPR Embedded Vision Workshop. Really kind of advanced the state-of-the-art on the trade-off between accuracy and speed and these problems. Runs quite well on mobile devices. And then we have SqueezeSeg, which is semantic segmentation for LiDAR. Sorry, people want to take pictures. I can wait. Yeah, pictures are good. Yeah. Cool. So the range of applications just gets broader from here. So SqueezeSeg, semantic segmentation for LiDAR. So this is classifying the type of every LiDAR point in terms of what object type it goes with. Required a lot of rethinking of the neural net design to make this work. And I think this is one of the, this was not just solving an existing problem better. This was framing a slightly different problem than people had been solving, oriented towards what we need for autonomous cars. So these and many other models comprise what we call the Squeeze family, which is a whole range of nets that Kurt and I and our extended academic family have developed over the years, most of which are open source and include training code and things and are easy to find online. We're certainly not the only ones who've been working on this, particularly since the SqueezeNet paper in early 2016. There have been a number of other efforts that have been quite successful. One of which that's worth mentioning is work by Andrew Howard and his collaborators at Google. So they have this family of work called mobile nets. And I think one of the most interesting things they did was to popularize an approach called depth-wise separable convolutions, which has basically just one channel per filter in the 3x3 filters. Papers describe it quite well, but that helped particularly improving the amount of computation required. They didn't optimize so much on the memory requirements, but as you can imagine, for each platform, your goals and trade-offs with those are different. So particularly for embedded processors on like ARM-based mobile phones using the CPUs, these are actually pretty good models. So one thing that sometimes happens when we talk about this stuff is people sort of conflate a pretty niche piece of the squeezing neural nets problem with being the whole problem. And what I mean by that is, so model compression. So sometimes when I talk about squeezing neural nets, they go, oh yeah, model compression, right? So model compression, basically taking a model that's been trained and then further compressing it by deleting parameters or reducing their bit width and things, is certainly a key part of the problem, and we do it as well. But to think that just taking a model like VGG or ResNet that's been trained in your application and compressing it will be optimal is not really true. So it's a bit like if you wanted to take a watermelon and make it fit into a smaller space, you just kind of take it with a hammer and kind of beat it, right? It'll help a bit, but maybe not exactly the thing you want to focus on. So deep neural net architecture search, or whatever method you use to discover brand new deep neural networks, tends to be, I would say, more the backbone and kind of the thing you want to start with. It's more like saying, I'll just grow the watermelon to fit the constraints that I've put around it. And then if I feel interested to beat it with a hammer later, I could go ahead and do that. I'm not trying to beat up a model compression. It's just kind of a memorable analogy, I would say. I borrowed this from Warren Gross at McGill and found it to be a bit humorous. So when it comes to architecture search, I think where a lot of people the hurdle you have to clear and the hurdle that people I think initially struggle with is, well, I got a deep neural net off the internet. It's kind of like a program. If I modify it, I might break it, so that's bad. Well, actually, deep neural nets comprise an infinitely large design space, and there are many things in the deep neural net design space that you can modify, which probably won't hurt much and might actually make things work better. So let me just talk about what some of those are. And to do that, I'll kind of introduce first the anatomy of a convolution layer. So convolution in deep neural nets, particularly convolutional neural nets for vision and 2D and 3D applications, kind of have a definition of their own. So the kind of core piece of this, kind of wander over here for a minute. So that orange box there, that's the data structure that these things are comprised of typically. So it's a tensor with a height and a width and a number of channels. And your filters look like that. Your convolution filters look like that. Your inputs look like that, and your outputs look like that. And then you have a series of kind of like matrix multiplications, but with a couple extra loops that run these filters, up and down, left and right on these grids. So when you start looking at a neural net and how to change it to use less resources, one thing that's definitely worth looking at is what's the height and width of your filters, because often what you might start with is overkill. So in convolutional neural nets, I often see people using 3x3 filters with 3x3 by number of channels filters for most of the net. And the reality is you want some spatial resolution in your filters, but you can get away with an awful lot of filters that are just one by one, where they're doing rotations across the channels of intermediate variables, but they're not aggregating across the spatial domain. And actually, you can replace a surprising number of 3x3s with 1x1s in most nets before the accuracy starts to degrade. And each 3x3 you replace with a 1x1 has 9x fewer parameters for that filter, and that adds up quickly. There's also what we call channel reduction. So reducing, basically there's this quadratic effect that people might, on the surface, mistake as being a linear effect, which is if I have a series of layers, I'll have the same number of filters. And let's say I start out with 384 filters per layer. And then so this orange box on the left, bottom left, that's a sort of a example net to start with that has a long series of filters that are, or layers that have 384 filters. If I change that 384 to 128, for example, cut it by a factor of 3, I have 3x less filters, but the surprising part for some people is I also have 3x less channels per filter, because the number of channels in your current layer is actually dictated by the number of filters in your previous layer. So this is sort of, you tune this knob a little bit, and the resource requirements actually tend to move wildly. So there's a lot more here, but to try to make some forward progress. So there's model distillation and compression. This is something I think that you want to do basically as a post-processing step. After you've discovered a net that works pretty well, you want to potentially train it to replicate a better net. That's the thing that actually helps quite a bit. I was actually skeptical of this area at the beginning, but this particular paper here, I think, has kind of proven in that this approach is really pretty effective and at least buying you a couple more accuracy points. So when you look at kind of the deep neural net architect's palette, if you will, a sampling of what's on there are 3x3 convolutions, pointwise convolution, depthwise convolution, which is where instead of having every filter span all the channels, you have the filters only span one or a very low number of channels. Channel shuffle and shift are both pretty recent innovations, relatively speaking, of how to get more mileage out of fewer filters and less computations. So these are the kinds of things people do. If you think about channel shuffle or shift, these were, again, recently invented. Anybody could invent a new one of these layers or tricks at any time, maybe you. So kind of integrating all this. So if you really want to do a deep dive on this stuff, there's like a 10-page-ish paper that Kurt and I wrote called "Small Neural Nets Are Beautiful." It was presented as an invited keynote at Embedded Systems Week 2017, and we kind of go through blow by blow what are the things that we know how to do, and then when you unify them, what's the multiplicative effect by doing all of them at the same time on reducing memory traffic, reducing compute, so forth, and how can we do that while minimally or not at all impacting accuracy. So taking a step back and thinking about this, the artistic process that engineers do to design a deep neural net, manual design, each iteration to evaluate a point in design space is quite expensive. Exploration tends to be limited by human imagination. Kind of go through this sequence of things, kind of look at the result, go back, try something else. And the question is, can we automate this? Or maybe more to the point, what aspects of this can we automate? So they're sort of led by Kwok Lee. There's a glut of papers lately on neural architecture search. Entertainingly, SqueezeNet was actually discovered by a relatively automated type of neural architecture search. When we published that paper, nobody really understood what that was about. Now everybody thinks, or lots of people think, neural architecture search is going to help. But one of the main issues is how do we do automated neural architecture search? We're going to search lots of models, but not spend kind of ridiculous amounts of computation. So there's this paper. I guess I didn't include the link, but if you Google DNAS, you'll find it, that my former lab mate Bi-Chen Wu, Kurt Keutzer, and some folks at Facebook did, called DNAS, or Differential Neural Architecture Search. And they're able to make incredibly fast progress in searching the neural net space with very little compute resources. There are a number of tricks they use to make it so the total amount of training you have to do to explore lots of nets is a lot smaller than you'd expect. And putting this in context, if you look at kind of the size of this, that's the amount of floating point operations, the amount of flops used to search the architecture space. And as you can imagine, it's not linear. A little bit bigger means actually way more. So that's the search cost basically in flops. The x-axis is computation, or sorry, the x-axis is computation, y-axis is accuracy. So where you really want to be is in the top left. And the DNAS stuff gets there with a minimal amount of computation. And actually starting, one thing you might ask is, well, did you just start with a really good net and improve it a little bit? No, most of these actually, including DNAS, start with a pretty naive net and rapidly iterate towards a much better net design. So this is looking at flops, which is an okay metric, but on different platforms, different types of operations, different matrix dimensions and so forth are cheaper or more expensive. Also, some platforms respond better or worse to reductions in flops. So one thing that my colleagues did in the DNAS work is to not just target flops, but actually in the inner loop of their optimization to look at how fast this actually runs, these different nets run on target compute platforms. And so what's interesting is the DNAS work discovers not just one net, but a range of nets that are good for different things. And the DNAS's kind of favorite net that hits this 73-ish% top one accuracy constraint on ImageNet for the iPhone 10 and the favorite net for the Samsung S8 are different. And if I have more time, I go into why. But basically, one of them is much more amenable to 5x5 convolutions. One's more amenable to 3x3s. And there are a bunch of other smaller effects as well that go into this. What's interesting is the iPhone 10 and Samsung S8 both use ARM-based processors. And it's just targeting the ARM processor for this, not the custom neural net accelerator yet. And even on almost this, what we think is a very similar computer architecture and a very similar memory subsystem and a pretty similar library, you get factors of 25% or more, depending which platform and which net combination. So I think this is a basic example of, for very similar platforms, choosing the right net for the platform is important. I think as we head towards this kind of, as Jensen Huang calls it, Cambrian explosion of different neural net accelerators coming out, we'll see wild, sort of wild swings in, for this neural net accelerator, you really want this net design. For that one, you want that one. And if you get them wrong, you're off by a factor of 10 in speed or something like that. So I'm getting towards the end here. I think the thing I'd like to encourage in the future is to see people start to break down the wall between deep neural net design and hardware design. One issue I see is there are deep neural net designers who they've realized that flops are kind of important, but the finer points like arithmetic intensity, otherwise known as the flop per byte ratio of the algorithm, floating point versus fixed point cost, how the memory really works, are kind of foreign, not something they're paying too much attention to. And then the hardware architects are kind of sometimes, often in no man's land, optimizing the crap out of sort of ancient history neural nets that have long since been abandoned or moved beyond. So what I'd like to see is these people kind of come together and jointly iterate on what do we want to compute, and then how can we get the hardware to do it and do that. If you look on Kurt's research page, we actually have done some work where we put hardware designers and deep neural net designers in the same room, and great things in some cases have happened. So I think I'm about out of time here. So key takeaways, kind of taking it from the top again to how we got to this part of the discussion here. Autonomous vehicles currently need a ton of compute hardware. Processing, literally computer processing, is on a trajectory of rapid improvement in operations per watt for neural net style workloads. But other aspects of the system that are not explicitly part of the processor, like memory, are improving much more slowly, and there are far fewer kind of breakthroughs projected on the horizon. Today's neural nets will be choked by slow memory on tomorrow's CNN accelerators. We're already seeing this, and I see an opportunity, a likely scenario actually, of it getting an order of magnitude worse or more just the next couple of years. And so I think the way to dig ourselves out of this is to design new neural nets that are smaller, kind of squeeze down all aspects of the algorithm as much as we can. They'll make full use of these next generation computing systems, reduce hardware costs of autonomous vehicles, and ideally enable lower cost, larger scale rollouts of autonomous vehicles and far more scenarios than just autonomous urban taxis. Thanks.
Thanks, Dr. Iandola, for a very interesting talk. We have a few minutes for questions. Who had the first one?
So, Jörg Basler, you have presented the problems that occur from transferring neural networks, which are basically a structure designed for biological hardware, onto a von Neumann architecture where we have processors and RAM, and then we run into all those problems that the processors are faster than the RAM and so on. Is there any serious approaches at the moment to implement those neural networks in suitable hardware structures that do not contain adders and multipliers, but that really execute the neural network as it is?
Sure. Yeah, let me look at that for a sec. So first of all, I think the bio-inspired aspect of neural nets are overhyped. So when you look at deep neural nets, I agree they're deep. I agree they're kind of networks. I don't think they're neural. I think they're actually a stack of glorified matrix multiplies. And so we actually know how to do matrix multiplies in hardware really well. We just don't know how to feed it with memory very well. So if you can make the matrix multiplies of sizes that fit in hardware well, Bob's your uncle. I think if you look at the neuromorphic computing efforts that are out there, I mean, there's IBM True North, which I think really hasn't gotten off the ground. There's some folks in San Diego who tried some things and really didn't go too far. I think we can do a lot of what we want with von Neumann architectures, and particularly fairly matrix-oriented computing. I think at least getting the stuff that I'm personally trying to run deep neural net-wise to run better doesn't require a full reboot of computer architecture. I think the open question is, is there an opportunity? Okay, so the thing we have to invent for your idea to work is a way for neural nets to sort of automatically figure out when to expand and how to allocate connections. Currently, that's all done based on neural architecture search or manually. So if that were to happen, and the connections turned out to be, having them in rigid matrices was just not what we want, then what you're doing is kind of interesting. But we actually don't know the right structures that would meet those, that would have those requirements yet.
Sorry, quick. Does the quality of the recognition by the neural net improve with the underlying image quality?
Oh, for sure.
Does the computational cost also decline if you've got a better image?
Mm-hmm. I believe that it does. I think from a couple perspectives. One, having just less images with less artifacts, right, is great. I think makes training easier, makes the end results better. I think second, if you can get more resolution, that sort of increases your degrees of freedom. And yeah, I think ultimately, your point I think is that if your images are better, you actually probably have to spend less computation, both at training and inference, dealing with artifacts, right? So I think yes.
And then just quickly, is there any quantification of that trade-off, or has that not been studied?
Good question. I think a lot of the mistakes, or like a lot of that trade-off that I've seen, has been less a function of making cameras, for example, way better, although I'm interested in that. And it's been more kind of when you see some sort of foul ball in terms of kind of smeared images from video artifacts or things, that's sort of a pain. So I think just getting everything up to a reasonable baseline is probably the first problem. And then, yeah, maybe we should talk offline. I don't know exactly what to ask for from the camera experts. Maybe I should have come in with that.
Fritz Lebowski, ST Microelectronics. Thank you very much for this wonderful talk, which stimulates very fundamental elements, which is the first component. How do you make people, the engineers of today, think differently, that they go your direction? And the second one is, with what you have today, how you make that transformation happen, that it fits in with that new logic. Do you have some thoughts to share about this?
Sure. So first of all, how do we get people from the neural net design, software implementation, and hardware communities working better together? I think the best way actually is to have a big challenge problem, like making cars able to see, and have those close collaborations be there in service of getting over some threshold of of trade-offs, right? Or achieving some set of trade-offs. And right now we're working with a number of hardware companies who are surprisingly receptive to our feedback on a frequent basis. And I think it's heartwarming that a 30-some-odd person startup actually gets to influence the next generation hardware of kind of 30-year-old hardware companies who do billions a year in revenue. I think it would be nice to be in a spot where I personally, we're involved in every aspect of the stack and building it. But as you can imagine, putting every single piece of that under the same roof can get really expensive for any one player. So basically, I think the collaborations that I'm describing are already happening. So sorry, your second question was?
Yeah, well, it's that incremental step, how you make the change happen, and you replied in it because you're saying you put challenges from where you are into the vision that you have to let the people just adjust stepwise.
Got it. Yeah. I think I saw one more question. Oh,
yeah,
great.
Yeah. So in terms of the model reduction, or in terms of image quality or imaging in general, so do you find color and resolution, do you see the difference between them? Can you, in your effort?
Could you be more precise?
So like is a three channel colors or half the resolution, which is better?
I see.
Like that, yeah.
So I think the reality is we don't necessarily have to pick because the imager isn't the expensive part anymore. So if we're looking at a 2K image, for example, and going, gosh, do we want to have a Bayer mask on here or not or whatever? Even the cheapest cell phones now and reasonably cheap cell phones 5 years ago had 4K imagers, right? That run at 60 FPS in some cases. So that's not a trade-off I find myself having to make in reality.
Okay. Just one comment, Forrest, regarding that cameras plus software might replace LiDAR as good as. Please consider joining our another keynote speech at 11:30. We'll have a speaker talking about solid-state LiDAR, and you might pose this question to him. So with that, let's thank our speaker again. And